Hello, we will now do the 7.3 worksheet, which deals with sampling distribution with means. And so I encourage you to pause this video and try a problem and then play the video and see if you get it right, and kind of, stop and start the video as you do the worksheet, and see if you can get this stuff right. But so let's look at this. So the first context says a company has packages of a vaccine that must be kept at very cold temperatures. The company has over 1 million of these packages. Their temperatures have a mean of negative 75 degrees Fahrenheit with a standard deviation of 4 degrees Fahrenheit. A company employee takes an SRS, a simple random sample of 50 of the packages, and finds their mean temperature. Describe the sampling distribution of the sample mean. Now, the sampling distribution is this. Okay, now so our population, the group that we want to know something about, is all of the packages, all of the million or whatever packages, and the parameter is the mean temperature, which the mean temperature of all of the packages is negative 75 degrees. But he takes a sample of size 50 and finds the mean temperature of those. Now, and so this is what we call a mu. That is the population mean. But the mean of the 50 is an X bar. It's probably going to be somewhere around negative 75, but not exactly equal to it, just because of random chance or sampling variability. If we took another sample of size 50, we get a different X bar, and another sample of size 50, a different X bar, and so forth. And if we found a large number of X bars, kind of every possible sample, this family of X bars we call a sampling distribution. Okay, it's every value S bar could possibly take in repeated sampling. Of course, and I talked about this in the 7.3 examples video. Okay, so we're asked to describe the distribution, so we have to cuss. We have to talk about its center, its unusual values, its shape, and its spread. Well, the center of the sampling distribution, which is the mean of the X bars, mean of all those X bars, is equal to mu, and that's equal to negative 75 degrees Fahrenheit. Make sure and put the units. All right, let's talk about the spread. Okay, the spread of the distribution is described by the standard deviation of the X bars, and that is equal to, and if you look at your formula sheet, so this is what I'm talking about here, sampling, this is the sampling distribution part, so sampling distribution for means. All right, so the mean of the X bars is equal to mu. The standard deviation of the X bars is equal to sigma over the square root of n. And so that's our little formula. And so it's equal to sigma over the square root of n. And so that would be 4 degrees Fahrenheit over the square root of 50. And so that is approximately equal to 0.565, 565,685, like that. Now, and so let's talk about the shape. Okay, the shape will be approximately normal. Okay, why is that? And that's because of the central limit theorem. Why is the sampling distribution approximately normal? Because by the central limit theorem, and you can just put CLT, our n is equal to 50, which is greater than 30. Okay, so the central limit theorem says is that the sampling distribution of X bars will be approximately normal if one of two things is true. Either your sample size is large, bigger than 30 or so, or if it's said the population varies approximately normally up here somewhere. Okay, so either one of those things can be true. And so that's why it's approximately normal. So in describing this, you would just say the sampling distribution is centered with a mean of negative 75 degrees. It has a spread, a standard deviation of 0.567, and then the shape's approximately normal, and that takes care of the unusual values as well by saying it's approximately normal. What fact allows us to use the formula for the standard deviation? And this is true for proportions as well. In order to use that formula properly, our sample size cannot be more than 10% of our population size. Okay, can't be more. And so in this case, it says there's over 1 million packages. So you would say there are over 1 million packages in the population And then so thus the sample size, which is 50, is less than 10% of the population, because we are not using sampling with replacement. We're using sampling without replacement. And in general, that's what we do. So, and so there you go. So those are two facts. When do we have normality? When can we use the formula for the standard deviation? Those are two important facts to know. All right, so then it says Julio is worried that the mean temperature of the packages is actually greater than negative 75 degrees. He takes a sample of 50 and finds their mean temperature to be negative 74.3 degrees. What is the probability that the sample mean of negative 74.3 degrees or more in a sample of size 50, assuming the negative 73 degree figure is correct? Does this give you reason to doubt the negative 75 figure? Now, and we're dealing with negative numbers here. So negative 74.3 is actually greater than negative 75. It's to the right of negative 75. So keep that in mind. All right. And so how do we find this? Well, we can use normal CDF. So we can use normal CDF, okay? And it says the sample mean will be that or more. So it'd be negative 74.3 degrees to infinity. And our mean is negative 75. And our standard deviation is 4 divided by the square root of 50. Make sure and label these. That's our lower bound. That is our upper bound. That is the mean of our X bars. That is the standard deviation of our X bars. And so what we're in essence finding here, so negative 74.5 is somewhere over here. I don't know exactly where. We're finding the probability of that or more. Okay. And then we're in essence, is this giving us evidence that this actual mean of negative 75 is wrong? Well, anyway, so let's do this with our calculators. And so to do normal CDF, we'll go second vars, which gets us the distributions, and go to normal CDF. And we are going from negative 74.3. So make sure you can hit the minus sign, that thing right below the 3, not this sign. Not make sure, don't hit the minus sign, hit the negative sign, which is below the 3. So we hit that. So we hit negative, and then 74.3 to infinity, or just some big number, so you can hit like 9 million or something like that. And so then negative 75, and then 4 divided by the square root of 50. So like that. And so we go like that. And so that, as it turns out, is 0.10796. 10796. And so that now, and so that is that area of that normal curve there. That number, that is the probability that, assuming negative 75 is right, that's the probability we would get a sample mean of negative 74.3 or more. And so, in other words, it would happen just by chance about 11% of the time. And so does this give us reason to doubt? No. Okay, no, because 0.10796 is greater than 0.05. So it would plausibly occur by sampling variability. If by sampling variability, in other words, just by random chance. If this probability here was below 0.05, that would give us reason to doubt this figure. In other words, our X bar would be so far out on the tail that it would be just really unusual for it to occur just by random chance. So that is that. And so then it says Julio increases his sample size to 100 and gets the same sample mean of negative 74.3. What is the probability that the sample mean will be that or more in a sample of size 100, assuming that negative 75 is correct? And does this give us reason to doubt the figure? So we'll do the same thing again. All they're doing is the same. All these things are the same here. They're just changing this to 100. So for this one, you would just say normal CDF from negative 74.3 to infinity, mean of negative 75, standard deviation of 4 divided by the square root of 100. So that's our lower bound, upper bound, the mean of our X bars, the sigma of our X bars, and let's see what we get. And so I'll just take this, I'll just arrow up and take that same command and just change this to 100, 100. And there we go. And so that, as it turns out, is 0.040059. That is below 0.05. And so, and once again, what that probability is, that's the probability that we're going to get a sample value this unusual, assuming negative 75 is true. And there's a less than a 5% chance it would happen. So does that give us reason to doubt the negative 75 figure? And say, you would say, yes, we do doubt it, because 0.040059 is less than 0.05. So negative 74.3 is unlikely to occur by sampling variability. In other words, just by random chance. And that, by the way, that logic is the basic logic of a hypothesis test, which we're going to do later in the year. All right. And so you'll notice when the sample size is 50, we did not reject. We did not have evidence to doubt the negative 75 figure. But when we increased the sample size to 100 and everything else was the same, then we get below 0.05, which would cause us to doubt that. Okay. So now let's look at the next question. So this one says this: why are the conclusions from number 4 and number 5 different, even though the sample mean is negative 74.3? Now, what's happening here is this: when your sample size is smaller, so when your sample size is 50, it's going to be your sampling distribution is going to be centered around the population mean. And here's all your X bars, okay, like that. So they're going like that. And they will vary approximately normal. When you look at all these X bars, they will vary, let's say something like that. When you increase your sample size to 100, okay, everything's else equal, you're still centered at negative 75, okay? But now the bigger sample size makes your X bars get closer together like that. And so it makes your tails in your distribution go down, and it makes it taller like that, taller and skinnier, okay? To where when you've got this value over here, so let's say negative 74.3 is right there, negative 74.3. In this curve, it happens like 10% of the time, according to the other side of the page. But on this curve, it happens very rarely. Okay, it happens less than 5% of the time. So the bigger sample size creates less variability in your sampling distribution. And so that's what this question is getting at. And so I've written this out here. So this is how I would say this. Why are the conclusions different? And that is this: the larger sample size, 100, creates less variability in the sampling distribution. So a sample value a certain distance above the mean, which in this case is 0.7 above, that's how far it is from negative 75 to negative 74.3, or higher, is less likely to occur. So with the bigger sample size, there's less variability. So values away from the mean are less likely to occur. So let's look at this problem here. In the context above, how large would you have to make your sample size if you wanted the standard deviation, the sampling distribution, to be at most 0.06? Now, once again, the little formula for that, the standard deviation or sampling distribution, sigma over the square root of n. So the standard deviation of my X bars is equal to sigma over the square root of n. It says I want this to be at most 0.06. So 0.6 rather, to be at most 0.6. And so this thing I want to be less than or equal to that. So our sigma is 4. And so how big does the sample size need to be? And so there's an inverse relationship between our sample size and our standard deviation, our sampling distribution. And it's inversely related by the square root. So anyway, I'll just solve this for the square root of n. I'll multiply both sides by the square root of n times the square root of n, like that. So this would give me that the square root of n times 0.6 is greater than or equal to 4. And so I'll divide both sides by 0.6. And so I get that the square root of n is greater than or equal to 4 divided by 0.6. And then 4 divided by 0.6 is 6.6 repeating. Right? And so so this would be the square root of n is greater than or equal to 6.6 repeating, like that. Then you square both sides, so n has got to be greater than or equal to 44.4 repeating. Now, your sample size has to be an integer, and you always round up. So by rounding up, I'm ensuring that the actual standard deviation of the sampling distribution will actually be a little bit less than 0.6, which is what I want. So you always round up, never round down. If you round down, then it could push this above 0.6. And so that's how you do that one. And then we've got this. So it says the mean of the weights of the apples in a farm is 14.8 and standard deviation of 3.2. The mean of the weights of the pears on a farm is 13.9, standard deviation of 2.3 ounces. A worker takes a simple random sample of 60 of the apples and an independent simple random sample of 50 of the apples. By independent, it's just saying that these two samples had nothing to do with each other and they didn't influence each other, which we'll talk about why that's important later in the year. He then finds the difference in the sample mean weights. Okay, so describe the sampling distribution. So we've got two populations here and two samples, and so let's record this down. So for the apples, it says the mean of the weights. So I'm going to just write that over here, just for my own sake, just to keep track of it. So the mean of the apples is equal to 14.8. Okay, and the standard deviation, the sigma of the apples, sigma sub a, which is 3.2, like that. And then so the mean of the pears, so I'll put mu sub p, is equal to 13.9. And then the sigma for the pears is equal to 2.3. And then it says it takes an SRS of 60 of the apples. So my sample size, my n for the apples is equal to 60. And my sample size is 50 for the pears. So my sample size for the pears is 50. And so there's my information. Describe the sampling distribution of the differences. And so what's happening here is they are subtracting apples minus pears. Okay, they're taking a sample of 60 apples, finding the mean. So that would be the X bar of the apples. And then they're finding an SRS of 50 of the pears and finding mean. So that would be X bar and subtracting them. And then so they're finding a difference, this difference. All right. So when you do that, when you find sample values like this, you say to yourself, well, that's one difference. Now we're expecting the difference, by the way, to be 14.8 minus 13.9. Okay, because that's the average of the apples, that's the average of those pears. So we're expecting the difference to be 14.8 minus 13.9, which is 0.9. So that's what we're expecting, but it's going to be off because of sampling variability. All right, so this is not going to exactly equal to that. Maybe it's going to be 14.7 or 14.82. It's going to be a little bit off that. This is going to be a little bit off from 13.9, somewhere around it. But when you subtract them, it's going to be somewhere near, but not exactly equal to. And if we took more samples and kept finding difference and took many samples and find many differences like that, it's creating a sampling distribution. It's every possible difference that can occur. All right, so the mean, what is the mean? So the mean of the differences, see, I tend to write mean of differences. The other way of, the more like on your formula sheet, so the mean of X bar sub 1 minus X bar sub 2, you just subtract the population means. And there's this, the standard deviation of the differences, X bar sub 1 minus X bar sub 2. It's equal to that formula there, okay? So you just plug in the values there. And so the mean of the differences is just going to be equal to 14.8 minus 13.9, which is 0.9. Okay. How do the differences vary though? The standard deviation of the differences is going to be equal to the square root of, and just plug it into that formula I showed you, 3.2 squared over 60, and then plus 2.3 squared over 50. And when you do that, you get approximately 0.525801, okay? And so that would be, so we're describing the distributions. We have to cost, we have to talk about the center, unusual value, shape, and spread. So the center is described by that mean. And then the spread is described by that standard deviation. The shape will be approximately normal. And why it's very important that you know why it's approximately normal. Because N sub A is 60. The sample size for one of them is 60. N sub P is 50. They're both greater than or equal to 30. So by the central limit theorem, our sample and distribution of differences has to be approximately normal. Both these numbers have to be bigger than 30, or it has to say up in the problem that both populations vary approximately normally. You have to have one of those things to be true. If one of those wasn't true, then you wouldn't have normality, okay? So if one of these sample sizes was below 30 and it didn't say up here that it varied approximately normally. And so that's in by saying it's approximately normal, and that takes care of the unusual values as well. So then what is the probability that the difference in the sample means apples minus pears will be more than 1 ounce? And so we can do normal CDF. So more than 1 ounce, that would be 1 to infinity. That's my lower bound. That's my upper bound. My mean, I just found that is 0.9. My standard deviation, which would be 0.525801. So that is the standard deviation of my differences. That is the mean of my differences, like that. And so let's see what this is. And so we shall go second distribution, normal CDF, from 1 to infinity. So this would be 0.9. And so this would be 0.525801. And so that, as it turns out, is equal to 0.42458. And so it's a pretty high probability. In other words, we wouldn't be surprised for that to happen at all, because this is certainly well above 0.05. Okay, that's it. That's it for the 7.3 worksheet. And I appreciate you watching the video, and I hope this makes sense to you. But please, send me any questions you have about this stuff, and I hope you have a great day.